All right. Professor Ghrist needs no introduction. He's a world-leading mathematician that has taken to very high levels the connections between pure mathematics, engineering, and technology. He is an expert when it comes to connecting deep theorems in algebraic topology and geometric group theory with solving problems in robotics, hydrodynamics, and information systems. At University of Pennsylvania, he is Andrea Mitchell University Professor with appointments both in the Department of Mathematics and Electrical and Systems Engineering. And I am deeply thankful to Professor Ghrist for having accepted to deliver this talk as part of the celebration of Simba staff's Department of Mathematics, and I warmly welcome him to deliver this talk.
Thank you very much, Jesus, for that introduction. Thank you very much for the invitation to those of you who are here listening, either live or over YouTube. Thank you for taking the time. I'm going to explain some applications of ideas from topology, from algebraic topology. But before we get into the math, this being applied mathematics, I really want to talk about the problem that inspires it first. And that problem is something from opinion dynamics. I'm going to give a brief overview and then we'll dive into the mathematics that we're going to talk about today. So what do I mean by opinion dynamics? Well, let's say that you've got a network, a social network of individuals who are tied together by some sort of friend type relationship. We're going to model that as an undirected graph. So think of something like Facebook, where it's undirected. You have to mutually friend with someone else. This is different than Twitter, where you can have directed follows that are not necessarily reciprocal. Okay, so we've got this graph of people, nodes, and connections, edges. And then what are we going to do? Well, let's assume that everybody has an opinion about something, some topic. Maybe it's, what do you think about the president? Or maybe it's, what do you think about the tie that I chose to wear today? It's a very kind of loud tie, but they say you're supposed to do that when you're being videoed. So that's what I did. Now you might have an opinion about this. Let's say you don't like it. Thumbs down, or maybe it's thumbs up. You do like it, or maybe you just don't care. One thing that we could do is topologize this space of opinions as the reals, so that there's a measure of intensity. You kind of like it or you really like it would be positive numbers, and you kind of don't like it or you really don't like it would be larger and larger negative numbers. And then 0 means you just don't care. So we're going to do things that way. And then the classic problem in opinion dynamics is what happens to people's opinions over time if you assume that they influence each other a little bit. So let's think about what could happen, what maybe does happen. Everyone starts off with their own natural opinion, their first impression, but then as they interact and influence each other, maybe you get to polarization, where there are subgroups of people that have very, very strong opinions. Or maybe you reach what is called a consensus state, where everybody's opinions sort of average out and modulate. Or maybe there are other things that could happen. Well, this field of study, opinion dynamics, is very old. There's some very nice classical results. I'm going to mention one from 1968 by Taylor. And what he did was he used the graph Laplacian to predict or model how opinions are going to change over time. Let me take a timeout, quick break, and remind people of the graph Laplacian. This is a standard construct in combinatorics or computer science, The graph Laplacian can be represented as a difference between a degree diagonal matrix and the adjacency matrix of a graph, or you can represent it in terms of boundary matrices. The idea is if you've got this graph, you label the vertices. The graph Laplacian is going to be a square matrix indexed by those vertices. And along the diagonal, it represents the degree, how many neighbors do you have, and off the diagonal, it records who those neighbors are. So this encodes a lot of structure of the graph. And this matrix is great. This is used all over the place in things like spectral graph theory, for clustering algorithms, for learning, graph signal processing, everything. Really, really fundamental. But way back, 1968, Taylor used this graph Laplacian to set up a network dynamical system. This Laplacian, just like the smooth Laplacian from calculus class, acts via diffusion. If you set a vector x that for each node records the person's opinion as a real number, as an entry of that vector, and then you evolve that vector over time according to the graph Laplacian. You have some little constant alpha, and then you say dx dt is minus alpha times the Laplacian of x. That's really a heat equation. And over time, those dynamics are going to diffuse opinions. Now that's a continuous time dynamical system. We could do a discrete time dynamical system by just doing a nice Euler discretization in time. And you get the following recurrence relation, where I is the identity matrix. In both these cases, discrete or continuous time, the theorem is that any initial condition, any initial opinion distribution is going to evolve to a consensus state where you have locally constant solutions over your network. So what that means is that over time, everybody agrees, as long as we just communicate. And the more we communicate over social networks, the faster you reach that consensus state. Now, if that sounds to you like it doesn't really correspond with what things are really like, now that we have things like Facebook, now that we have things like Twitter, having everybody agree the more we communicate is not exactly what we see. So how do we deal with that? Well, this is a very old result, and there's been a lot of work done since then. It's impossible to survey everything that's been done, but let me mention a few things. A lot of work is focused on what happens when you don't just have one subject for opinions, but you have multiple opinions. There are generalizations of the graph Laplacian that work really well in that setting. There are different dynamical models than just straight diffusion, something called bounded confidence or Hegselmann and Krauss models, where you only influence a neighbor if they're already kind of close to your opinion. Otherwise, they don't listen to you. That, of course, can lead to some interesting polarization. There are many, many, many more models out there. You got one model for this type of behavior. You got one model for that type of behavior, another model for another type of behavior. A lot of the techniques vary as well, everything from game theory to differential equations. But most of the current work that is out there seems to be based on graph theoretic methods, with the graph Laplacian playing a really important role. Many of the works that are out there, especially recent works, have increasingly complex models that lead to increasingly complex behavior. My goal going into thinking about this subject, which I've only somewhat recently gotten into, my goal was to come up with a very broad but a very simple model. And the techniques that I and my co-author Jakob Hansen brought to bear on this are coming from Sheaves and Sheaves Cohomology. And this is where we get to the interesting topology. So now I want to take a few minutes, having done background on opinion dynamics, let's do some background on sheaves and sheaf theory. Very cool part of mathematics, but not as well known as it ought to be. It's a little bit intimidating. What's a sheaf? In its simplest form, a sheaf is really a data structure, something that pulls together algebraic data over some sort of base space, some base complex. In the simplest applications, in what I'm going to talk about today, that base space is just going to be a network, a graph with vertices and edges, although many more complicated things are possible. That data, that algebraic data, is also going to be as simple as possible, going to work with vector spaces and linear transformations. So in everything that we do, even though it can get more complicated, you should just think of a base space as being a network with vertices and edges, and you have data sitting on top of those entities. The data is in the form of vector spaces. And in the same way that the graph consists of vertices that are glued together with edges, the sheaf, the data, is a whole bunch of vector spaces and a whole bunch of linear transformations that connect them according to the pattern of that base space. Now, that's the simple example. The more general context in which I'll be speaking is cellular sheaves, which themselves are a simplified version of the more general topological sheaves. In its simplest form, a cellular sheaf has as base space some cell complex, maybe a simplicial complex, maybe something more general. And that sheaf is a functor from the face poset of that complex to the category of vector spaces and linear transformations. And this means exactly what I just said earlier. To every cell, to every vertex, edge, to simplex, you associate a vector space, and you have linear transformations between these that glue everything together according to the usual conditions for being a functor. These vector spaces, this algebraic data we call stalks, and the maps that connect this data are something like compatibility constraints. They're saying if you choose vectors, if you choose bits of data over the vertices, do they match along the edges? Do they match along the higher dimensional cells? Now, that's what a cellular sheaf is. These transformations go from vertices to edges to higher dimensional cells. There's also a dual notion of a co-sheaf that reverses all the arrows, that reverses your functor from covariant to contravariant. Co-sheaves, also important, also really cool. For today, we're just going to work with sheaves. Now, what are we going to do with them? Well, if you've seen some of the other talks in this series, if you've seen some of the other work in applied algebraic topology, you know that things like homology are really, really useful, and that spaces and their homology is a thing that you can compute. Well, we can do the same thing for sheaves. Sheaves themselves have something like a homology theory. It's more natural to do this as cohomology. And let me tell you briefly how sheaf cohomology works. What we're going to do is we're going to take our cell complex X, maybe a graph, maybe something more complicated, and for each dimension of cell, we're going to bundle together all the stalks over all of those cells. So we're going to take all of the zero-dimensional data, all the data over the vertices, combine it into one big vector space via a big direct sum. We're going to do the same thing with all the data over the edges, all of those stalks, put them together, one big vector space. Do the same thing with higher dimensional cells if you have them. And then all of these linear transformations that go from vertex data to edge data, we can combine into one big linear transformation that acts like a co-boundary map, that is a co-boundary map, using a formula that's very similar to what you do in elementary algebraic topology. When you set all this up, then you get a nice cochain complex of vector spaces. You can compute kernels mod images in order to get a nice, well-defined cohomology theory for this sheaf that compresses out all of the redundant data and just gives you the important stuff. Now, trying to interpret sheaf cohomology, that's non-trivial. The place to start is with the zero-dimensional sheaf cohomology. This H upper 0 is often referred to as the global sections of the sheaf. They are choices of data over the vertices that match over the edges. It's a compatible choice of data. The higher dimensional sheaf cohomology is, as with usual cohomology, giving you obstructions. They're telling you whether it's possible to solve certain problems or not. But almost everything that we're going to do for the rest of today just uses H upper 0. So we'll just leave it at that for now. Okay, so that's opinion dynamics on the one hand, and that's cellular or network sheaves on the other hand. What are these sheaves good for? Are they applied? Are they useful? Oh, yes, absolutely. There are several historical applications of these sheaves, of these cellular sheaves, or sometimes co-sheaves, often in contexts where that language really wasn't even used. In some cases, it was researchers saying, hey, look, there's this really interesting homology theory that I just made up. I wonder what it means. And it turned out to be something like a co-sheaf homology or a sheaf cohomology. In recent years, there's just been a bit of an explosion of examples of these cellular sheaves being useful in a number of different contexts. And what I want to talk about today is one particular aspect of these sheaves that really makes it useful. Some of what's useful about these sheaves is just structural in nature, in the way that category theory is often useful from the perspective of structure. But there's more. You can do geometry with these sheaves, and it's a beautiful thing once you introduce the notion of a Laplacian. What do I mean by that? We've talked about the graph Laplacian, right? Ooh, we can update that. We can modify that to sheaves. There's a classical application of Laplacians in sheaf theory that comes from differential forms and Hodge theory. If you have a, let's say, compact finite dimensional manifold, you can look at sheaves of differential forms on that manifold. You can build a cochain complex using the exterior derivative D. With a little bit of geometry, you can use a Hodge star, take the adjoint of this, and you can form what is classically known as the Hodge Laplacian, using the formula d star d plus d star. Now, maybe you've seen this before, maybe you haven't. If you haven't, don't worry about it. But it's a classical result that if you look at the harmonic forms, things that vanish when you hit them with the Laplacian, then you get the cohomology of your manifold in real coefficients. You can understand the topology of the smooth manifold via its harmonic forms, via the Hodge Laplacian and its kernel. Now, what we're going to do is update that story, not to sheaves of differential forms, but to cellular sheaves with data taking value in vector spaces. Remember, when we were doing sheaf cohomology, we have this nice cochain complex. Well, if we add a little bit of geometry, let's say we have explicit bases on the vector spaces that we use for our stocks, so that we can take adjoints, so that we can take a transpose of a matrix. Then, in that case, we can compute an adjoint to the coboundary operator. We can compute the transpose of this thing represented as a matrix. That gives us enough data to be able to define the same type of Laplacian operator. This is the Hodge Laplacian or the Sheaf Laplacian that is just the coboundary operator plus its adjoint squared. Now, this really is a generalization of this classical graph Laplacian. Why is that? Well, if we had the simplest possible sheaf over a graph, let's say it's just the constant sheaf, you have a one-dimensional vector space over each vertex, over each edge, over higher dimensional cells if you have a higher dimensional complex, and the maps that glue them all together. All of these linear transformations, they're just the identity map. If you're in that context with that trivial sheaf, then this sheaf Laplacian is the graph Laplacian in 1D, or it's the simplicial Laplacian of Ekman in higher dimensions. But now we can make sense of this where we have wildly different vector spaces from vertex to vertex, from edge to edge, where the vector space transformations, the linear transformations that glue it all together, they can be very, very different. And yet we still have a Laplacian, a Hodge Laplacian, and the kernel of that Laplacian computes cohomology. Cohomology of the base space? No. Cohomology of the sheaf. So we can get at sheaf cohomology by computing harmonic cochains. And this is great because we now have a lot of geometry that we can work with. If we're in grading 0, if we're looking at data over vertices, then we can use that zero-dimensional Laplacian to compute an inner product, something that gives us a way of saying, how far away are we from a zero cochain being a zero-dimensional cohomology class, from being a global section? And this operates very similar to the way that the graph Laplacian tells you how close your graph is to being disconnected. Okay, that's the background. That's all the tools that we're going to need for doing some more serious work. What I'm going to talk about next is joint work with Jakob Hansen, who is a very smart postdoc at Ohio State University, who did his PhD at Penn with me a year or two, a couple of years ago. He graduated in 2020. Time is all nonlinear now. Okay, what is it that we have done? We have defined a class of sheaves that is custom built for talking about opinions and opinion dynamics. Here's how it works. Let's say that we've got a graph, a social network, and I'm going to put a sheaf of vector spaces over top of it in the following manner. Over each vertex, we're going to have a vector space of opinions, an opinion space that comes with a basis of topics on which you have opinions. But here's the thing. This can vary from vertex to vertex. I've got things that I really care about, that I have opinions about. And you have things that you really care about, that you have opinions about. But it's not necessarily the same as mine. It could be totally different. Maybe I care about a lot of things. Maybe I care about few things. Everyone gets their own opinion space. But when we're talking, when we're discussing and trying to formulate an opinion on some topic, well, it might not be related to my opinions. It might not be related to your opinions. It might be, it might not be. We might be talking about something that's totally different. So over that edge that represents our discussion, our discourse, we have a stock, we have a vector space that itself comes with a basis of topics under discussion. The linear transformations, the maps that go from the vertex data to the edge data are expressions. They are formulations of opinions based on personal feelings, personal internal discussion. that is really adapted well to how a sheaf works. The idea that you can do different things all over the place. Here's a somewhat explicit opinion with apologies for potentially making you hungry. Let's say that you and I are talking, and we're talking about whether we should walk to town and get some lunch. Now, I'm not there with you in person, so sadly, we can't actually have this discussion. But let's pretend, and you've got some opinions on the matter. And maybe the things that matter most to you are whether or not you like to walk and whether or not you're hungry. And maybe at the moment, you're not in the mood for walking, but you are kind of hungry. So you might formulate an expression of an opinion that is weakly positive. Yeah, I might like to walk to town and get some lunch. On the other hand, my opinions have nothing to do with these topics. My opinions are all about food. I have strong opinions about tacos. I have strong opinions about cerveza. And I'm thinking, yeah, let's go to town and get some tacos and cerveza. I would like that. By the way, I'm making tacos for dinner tonight. I'm cooking up some lengua, and they're going to be, oh, it's going to be so good. I'm thinking about it right now. That's why I've included this example in this talk. So I'm thinking about those tacos. I have a very strong opinion about this. As you can see, this is a stupid example, but this is a very flexible model. Now, imagine I'm having lots of discussions with lots of different people. We could be talking about all kinds of different topics, and I'm formulating different expressions of opinions. With the flexibility that linear transformations have, I can modify my opinions depending on who I'm talking to. I don't necessarily have to share my private opinions. Or if we are talking about something that is one of my private opinions, I might even lie. That's what would happen if I put a negative sign in front of one of those linear transformations. In fact, one of the things I like about this model is that all these mathematical artifacts have very explicit interpretations. So the zero cochains are opinion distributions. They're private opinions over the vertices, over the people. One cochains are public discussions. That coboundary operator, that's something that measures the total amount of public disagreement. The Laplacian, the sheaf Laplacian, is something that's focused on vertices, and it measures average private disagreement. How much am I in disagreement with the average of my neighbors? And the zero-dimensional cohomology, the global sections, these are literally harmonic opinion distributions. This is the kernel of the Laplacian. And so these global sections represent opinion distributions for which there's public or expressed agreement, even though all the opinions are private. Okay, now we've got enough to be able to do some math, to prove some theorems. Do you remember that old result of Taylor that I started off telling you about? Here's a modern update for that. If you use the sheaf Laplacian on one of these discourse sheaves to set up a heat equation for opinions as zero cochains, that's going to look like dx dt equals minus alpha times the Laplacian of x, where again, x is a zero cochain, a distribution of private opinions. Or in discrete time, could do just like we did before. These are the exact same equations, but now this Laplacian is a sheaf Laplacian. Then, same as before, every initial condition converges exponentially to the closest harmonic opinion distribution, to the closest global section. So we head towards a consensus state, but not a rigid, everybody believes the same thing. No, it is an expressed consensus where personal opinions are still private. Now, what do I mean by closest? I mean via orthogonal projection to the space of harmonic zero cochains. We have a geometry on everything that we're doing, so this all makes sense. Is this a hard theorem? Nope. No, it's not. You got to show that the sheaf Laplacian is just like the graph Laplacian, positive semi-definite. And then the rest is a spectral argument. Okay, now this sounds pretty cool. What does it mean? Does it mean that everybody agrees? No, not necessarily. Everybody's still got their private opinions, but the public expression has consensus associated with it. Okay, that's the first of many results that one could prove. Now, I'm going to take just a couple of minutes and talk about a few extensions of this that show off a little bit of the flexibility of this model. The next thing I want to talk about is what happens if you've got some people that are stubborn, that don't want to change their mind. They'll listen to you, but they're not going to change. They're just, nope, they're stubborn. Maybe this is just someone who's naturally stubborn. Maybe it's an intentional propagandist. Maybe it's one of these bots on social media that just puts out disinformation and itself is never influenced by the discussion. How do you model something like that? This is not difficult at all using what we have set up. All you have to do is modify these heat equations so that you've got the standard heat equation with the sheaf Laplacian, as long as you're not one of these stubborn agents. Let's bundle all of those stubborn people together into some subset U. And on U, we're going to zero out the dynamics. Just kill it. They are inflexible. What do the dynamics of this look like? Well, it's not obvious unless you have this language of Laplacians and harmonic cochains, in which case it is obvious what to do. It is obvious what to try to prove. Because if this were in some smooth setting, what would you be looking at? You'd be looking at harmonic extension. And so adapting that intuition, what we guess and what is true is that every initial condition now converges not to the closest global section, but to the closest harmonic extension of the opinion distribution on the set of stubborn agents. There's some more results that undergird this. Jakob Hansen in his thesis proved that such an extension always exists, and it's unique if a certain relative cohomology, a relative H upper zero, vanishes. So we can say exactly what is going to happen, and we get a nice uniqueness result when we have this obstruction vanishing. And that's just the beginning of a whole bunch of interesting questions having to do with propagandists, with stubborn agents who are injecting their opinion into the system and not being influenced by it. What happens if you start applying some control theoretic perspectives? What happens if we set up something like a classical control theory where we have user inputs, where we have observables? Well, there's a fun story here, all the details of which I'm not going to go over, but the idea is that if you want to drive a particular outcome in a social network, and if you know enough about this sheaf, then there's quite a bit that you can do. If you've got a harmonic distribution, what you get after flowing via the Laplacian, and you have a set of stubborn agents, propagandists, call them U. They don't have to be connected like this. I've just drawn that as an illustration. And if you have some other subset of observables, of people that you want to focus on, you want to look at their opinions and drive them, then the relative H upper zero of X rel U in this sheaf cohomology that's the obstruction to the controllability of the system. Whereas if I look at the relative H upper 0 of X rel Y, these observers, then that's the obstruction to observability. If both of these relative cohomology classes vanish, then you can program the outputs to be whatever you want. Given inputs, it will drive the system to a unique state where you have guided those observers to have exactly the opinions that you want. Now, that's a little creepy sounding. So it is at this point that I should remind you that this is not a terribly realistic thing. Being able to compute this would require having lots of information about the entire social network and about how people represent their internal opinions, how they express opinions on topics of discourse. I cannot see a realistic way to implement a control like this. But it is fascinating that you can prove theorems about controllability and observability with this model. Now, let me take the time to critique this model a bit further. Well, we've been assuming that people can change their opinion based on discussion, based on discourse, that people are flexible. I'm not so sure that's a really good assumption. Is it realistic to posit that people's opinions are going to change based on just discussion? Let's go back to that stupid toy example about getting some lunch. According to this model, what is happening if we are discussing what to do about lunch? According to this model, it's the zero cochains that are being updated. So you would be actually modifying your opinions on how much you like to walk and how hungry you are. I would actually have to be modifying my internal opinions about tacos y cerveza. I'm not sure that that's accurate. Now, it's nice for a model, it's nice for proving theorems, but I think that something maybe a bit more realistic would have to do not with changing internal opinions, but rather changing how those opinions are expressed. And the cool thing, maybe the coolest thing I'm going to tell you today, is that that too can be modeled using these sheaves. Instead of putting dynamics on the space of zero cochains, we can put dynamics on the space of discourse sheaves, where what is changing over time are the maps, the linear transformations from vertex data to edge data. We're changing expressions of opinions. Here's a really cool theorem. If you start off with an initial condition, an opinion distribution, and you set up a heat equation on the expression of opinions. So this guy here, this F, is the map that takes you from data over a vertex V to data over an edge E. It's an expression of my opinions in talking to you. If we flow that by a heat equation, and I've written it without the Laplacian in there, but you can write it with the Laplacian. This really is a heat equation. Then this dynamics is going to have a system that converges to the closest discourse sheaf on which that initial opinion distribution is a global section. This is very cool. There's some details in there as to what I mean by closest. You can see the preprint for those. But this, I think, is quite a bit more realistic. Let's say we set up a really simple discourse sheaf. Everyone has one opinion. What do you think of the ruler, the prime minister, the president? And we're discussing that exact same topic, and we're just expressing our opinions naturally. There's no there's no disguise, there's no ambiguity. Well, maybe we have a setting where, people don't agree as to whether the president is good or not. But under these dynamics, what happens is not that people change their opinions. Rather, you have a big disconnect between your neighbor, and as you keep talking, you sort of tone it down a little bit until you both bend in your expression and you agree. And then you talk to the other person that maybe has a totally opposite opinion. And in this system, when we simulate this, people keep their own opinions, but they learn how to lie. They learn how to exaggerate or dampen what they say in order to have everybody get along. I think that having that as an ingredient along with changing internal opinions, I think that's a much more realistic model for how opinion dynamics over networks actually works. Now, most of these examples I've given you, they're very cartoonish. In fact, the model itself, the dynamics, is really fairly simple. This work began just as a way to explain or motivate network sheaves. I think there's a whole lot more that one can do as far as making more realistic versions of this, implementing, say, nonlinear dynamics so that you really get some interesting stuff happening over time. But a lot of these are open questions that are available for people to look at. What I'd like to end this talk with, if I can have your patience for a few more minutes, is to think about the sheaves themselves and to think about moving beyond the category of sheaves in which we've been working to something much richer that will have more modeling power and be mathematically much more challenging and perhaps interesting. What I'm about to go over quickly is joint work with Hand Riess, who is a PhD student of mine in electrical and systems engineering at Penn. And what we have been doing is, instead of working with sheaves of vector spaces and linear transformations, we've been working with sheaves of lattices. These are algebraic lattices, not the geometric lattices that you may have seen. What do I mean by a lattice? I mean, roughly speaking, a poset with an explicit pair of operations called out, something called a join and a meet. These are generalizations of max or union or least upper bound and intersection and min and greatest lower bound, respectively. These are going to be the stalks over our vertices, over our edges. They allow you to do very, very rich modeling, to have internal logic that is more than just greater than or less than. Now, to map between lattices, they very conveniently come in adjoint pairs. Every connection, sometimes called a Galois connection, between lattices comes in a forward and backward pair. And that's going to be very nice for us as far as trying to do Laplacians, Sheaves cohomology, all of that. Now, it's kind of tough because this category of lattices and Galois connections, it's not an abelian category. We can't do Sheaves cohomology. We can't set up a Hodge Laplacian based on the cochain complex because we don't really have it. But what we can do is define something that is morally a Laplacian, that feels like a Laplacian. This is something that Hans and I call the Tarsky Laplacian, based on old ideas or old theorems of Tarsky on dynamics on lattices. Let's say you've got a sheaf of lattices on a graph, and you have a zero cochain, a choice of lattice element over every vertex. Then the Tarsky Laplacian is going to act on those zero cochains via the following formula, where that symbol there, that's a big old meat. Now, what is this? Is this a Laplacian? It doesn't look like a Laplacian. Ooh, it really is the right analog of a Laplacian. If I pull out what is happening local to V and what is happening with respect to V's neighbors, where V is a vertex, then this decomposes the same way that the graph Laplacian does into a diagonal degree matrix and an adjacency matrix. But now we have an expansion component and a mixing component, just like the graph Laplacian. And just like the graph Laplacian, we could prove theorems with this about diffusion dynamics. Here's the hard result. If you have a sheaf of complete lattices on a graph, then the global sections, the choices of vertex data that are consistent over the edges, this is computable via Laplacian dynamics with this Tarsky Laplacian. If you take the fixed point set of the identity map wedged or meted with the Laplacian, then you get the global sections. And that fixed point set is what you get if you iterate the Laplacian over and over. You can compare it with that discrete time heat equation, and it's exactly the same thing. So you could take any cochain you want, iterate the Laplacian, it will converge to a global section. So this gives you a really nice distributed method for computing the zero-dimensional cohomology. And it also gives you a non-trivial result about these global sections being a complete quasi-sublattice. Totally not obvious from the beginning. Now, I think this is going to be a really good way for modeling opinion dynamics, other very, very rich structures over social networks, and using Laplacian dynamics to come to consensus in these settings. On the math side, I think this opens up a whole bunch of really cool questions. We can't define the higher dimensional cohomology, again, because we can't build a cochain complex. We can't take kernels, mod images, but we can define the Tarsky Laplacian. And so let's pretend that Hodge theory works. And let's assume a Hodge theorem in order to define cohomology. If we have a sheaf of complete lattices on a cell complex, higher dimensional base space, then that Tarsky cohomology can be defined in terms of the Tarsky Laplacian. We're going to take the fixed point set of the identity, meet that k-dimensional Tarsky Laplacian. We're just going to call that the Tarsky cohomology. Is it an honest cohomology theory? Nope. No, it's not. No way to make sense of it under the structure that we have, but it is a non-empty complete quasi-sublattice, and there's some interesting stuff going on there. That is one of several open directions for the future. My group is currently working on extending these Laplacians out further to looking at sheaves of more general categories and weighted categories over graphs. That work in particular is being done with Hans, with Paige Randall North, and with Miguel Lopez. All of the work that I've talked about today is joint with various persons from my group. I am so grateful both to them and to the United States Department of Defense, which has been generously funding this work. But most of all, I am grateful to you for sitting through nearly an hour's worth of very fast talking about sheaves and opinion dynamics. Thank you very much.
All right, may I ask everyone to please unmute yourselves to express our gratitude to our speaker? All right. I think we have a few minutes for opening up a session of questions. So please, if you have a question, go ahead. Well, I do have a question. Well, actually, two comments or questions. And essentially, this is related to products and coefficients. So let me say I go back to Sheaves Cohomology, and I believe you're measuring opinions over the reals. So the first question would be if there is any difficulty or any gain in using torsion coefficients, and also what happens if you if it has any meaning to understand cohomology operations. I'm thinking, for instance, in terms of cup products, where you would be using two different sheaves of discussions, and then if you some kind of sense out of these structures in algebraic topology.
These are both great questions, and they are, at least the second one is very strongly predicated on other questions that have not yet been answered. So let me start with your second question first. That is in terms of cup products. I think that would be fantastic, but what we would need first is a really good understanding of what these opinion dynamics look like when you're over a two-dimensional base space. And I'm not so sure how to make sense of that. On the one hand, of course, cellular sheaves over higher dimensional complex, oh, that makes sense. And we have to have the functor conditions so that the opinions over the vertices sent to the edges, when you send them to the two cells, no matter how you get there, they have to agree, they have to match. But what that really means is that agreement in the sense of a global section, in the sense of zero-dimensional cohomology, really only depends on the one skeleton, and the two skeleton is irrelevant. So you really need to talk about harder problems in order to require one-dimensional and two-dimensional cohomology classes to solve. And these haven't really been worked out to my satisfaction. But I have some problems even before that with the sheaf condition over a higher dimensional base space, with the idea that things have to match up. And my problem is I observe in social discussions the phenomenon that sometimes occurs that when we have pairwise discussions, let's say between faculty in the department, and there's general agreement, and then we get everybody together to discuss en masse, and then there's not agreement. I think there's a difference between consistent pairwise discussions and the sort of three-way, two-simplex discussion, to the point where I think the right model would be to break that functoriality and look at something like a sheaf in that broken context. That's not something that I've done, but I think it would be really interesting to do. And I think you have to answer those kinds of questions before we can get to the cool stuff that you asked about. As to your former question with torsion coefficients, wide open. I haven't worked with that at all. I think it would be really interesting, but I'm not sure what it would mean in the context of the social network, of the opinion dynamics.
It would be some kind of quantized opinions, I would suppose, but then there's some kind of cyclicity. I have no idea.
Yeah, I'm not sure.
All right. Anybody else? Well, I think this is a good moment, please, to stop the recording.
So